All right, ODP 206. We're working with a different type of struct node which has only two fields, an integer field and a pointer to a struct node field called next. So similar to the one we were using for PA1, but there's no valid field here. It's just data and pointer. And the pointer, instead of being an int, it's a struct node star. So let's look at that. So struct node is an integer and a struct node star. Sorry? This is for 206, this is for PA2 eventually. Alright, so data and a struct node. So the function you're writing for this ODP new node basically allocates a new node, initializes the data to the value you pass, initializes next to null, and then returns that node as its value. So your function has a prototype like this. It takes an integer, it returns a struct node star. So it's actually returning a pointer. So how do we create a new node? You call malloc. Okay, the purpose of malloc is to find memory in space, return the address of the beginning of some block of memory. So we want a block of memory that can hold a struct node. So we want to call malloc size of struct node. And that's going to return a struct node star. So we can say something like PTR, which is a pointer to a struct node. PTR equals malloc.
Could you also do in the size of just say pointer?
No, so I was about to say that. You don't want to do size of struct node star. Because struct node star is a pointer, it's an address. The size of a pointer is 8. Whatever your structure is, size of that structure star is always going to give you 8. And in our case, we probably need at least 12 bytes for a node. And if we had more fields, we might need 112 bytes. And size of struct node star would just give us 8. And size of PTR, since PTR is a struct node star, would just give us 8. Technically, you could probably do size of star PTR, but don't. Okay, I'll stick to my suggestion yesterday. Never put variables in here. Just put in types, because then it's less likely to be confusing what I'm asking for the size of.
You haven't set PTR anything yet. If you stated star PTR, wouldn't that throw you?
I'm not sure. I've never tried. It might open a black hole and kill us all.
The assess function doesn't catch it if you put the variable in there instead.
Yeah, I know. It's very possible to do things that aren't quite correct and have the assess function work. Because if I allocate 8 bytes, I actually get 32 bytes. And that's enough space for a struct node. Yeah, I think it likes it. That actually works, but don't do it. All right, so we malloc size of struct node. That gives us an address and stores that address in PTR. Okay, technically it's possible to run out of memory. It's possible when we call malloc, there may not be enough space to satisfy our request. If the system cannot find this much space to give us, that's an error, we're out of memory. What do you think malloc returns in that case?
Nothing or no?
Null. So technically, anytime you call malloc, you should do this check. And if pointer is null, it means you're out of memory. If you don't do that check and pointer is null and then you try to do something with pointer like dereference it, you'll get a seg fault. And your program will exit. But it's nice to get a message here saying out of memory. Just in case. It's a return or exit or whatever. All right, so assuming that we did not run out of memory, PTR is now one of these things. And we could give a value to the data field. Like that. And that puts a value in here, and so on. Now what happens if we don't do this first? If we don't set pointer equal to malloc and we just say pointer arrow data equals something, what's going to happen? Say struct node star pointer and then pointer arrow data equals 42.
Gonna set the data field of pointer to 42.
Okay, where is that going to be in memory?
The address of pointer will be the first.
So what's the address of pointer though? We don't know, right? We haven't given pointer a value. This is like saying integer I, print I. What's it going to print? Don't know, because we didn't give I a value. Struct node star PTR, we don't know what the value of PTR is. We've said it's a pointer to a struct node, we haven't given it a value. So now we're saying whatever value PTR is, go to that location in memory, treat that as one of these nodes, set the data field equal to 42. Well, we have no idea where in memory it's going to go. If pointer is 0, it's going to try to go to location 0 and pretend that that's a struct node and set the data field equal to 42. All right, so let's compile that with GDB. Well, if we look at PTR, it's a struct node pointer, and its value is 0. And if I look at what's stored at that address, it tells me I can't access it. So if I try to execute this pointer arrow data equals 42, I get a seg fault. It's trying to access memory location 0. So malloc size of struct node. So So PTR is 0 to start. Call malloc. PTR is now equal to crazy number. And we set the data field of a node stored at crazy address equal to 42. So now if we examine this memory location, there's our 42, 2 times 16 plus 10, and there's the next field, and then there's whatever comes after.
And we can set pointer next in the same way we set pointer data.
Mm-hmm. So we can set pointer next to be dead beef. Arrow next. So there's pointer, crazy address. Set the data field equals to 42, set the next field equal to dead beef. Let's examine memory. There's our 42, there's our dead beef. So the address is actually 8 bytes. So the 4 low bytes are dead beef and the upper 4 bytes are 0, because the 0 extends our number that we put in. And then what comes after that, who knows? It's unaffected. So this structure looks like the structure we were using in PA1, structure we were using in the earlier ODPs, but our variables are always going to be pointers to structures. And so to reference a field, we're going to have to use the arrow to dereference, and then the name of the field, so like so. So let's take a quick look at yesterday's ODP. So that was the set function, and the goal was to take a data value, double it, and then set the next field equal to null. And define the struct node, right? So it's got the 2 fields, and then the set function, its type that it returns is void, which means it doesn't have a return value. So you can't say I equals set, blah, blah, blah. You can just call it with set. The argument is a struct node. I called it in. So in arrow data means the data field of the thing pointed to by in, multiply by 2, store that in the data field of the thing pointed to by in. That doubles the data. And then set the next block equal to null. So if in looks like this, set would change this to an 84 and set this to a null. And I included stdio.h because that's where null is defined, or from something included in there. And when we're dealing with pointers and we want a 0, use the symbol null, N-U-L-L uppercase. Okay, it's not the same thing as 0. It's not the same thing as single quote \0. Okay, don't use those if you're talking about a pointer and you want that pointer to be null. Use the actual word null. If you use a 0, if you use a quote \0, it will probably work, but you'll probably get warnings from the compiler, and in some cases you may actually get errors when you run. So stick with null, because null on this system, it means 8 bytes of 0. Quote \0 is 1 byte of 0. And will it fill in the other bytes with zeros? You hope, but no guarantee. By the way, I did get yesterday's video uploaded, so I uploaded it this morning. And I have a flash drive that's fast, so I'm putting the lectures on there and then uploading them in my office. So we're not dependent on Wi-Fi. All right, so that works for 205, and that's similar to what you can do for 206. 206, the only big difference is you have to malloc a new node. What you don't want to do in 206 is the following. So don't do this.
This is from 205, right?
This is from 205, yeah. All right, so 206, we're making a new node function. So, and it's returning a struct node. Okay, so don't do this. This may look like it works, but I've tried to make the assessment test bed so it will fail if you do this. The problem here, what's the problem here? You tell me.
You pre-allocated whatever temp is.
We've pre-allocated whatever temp is, exactly. This is a local variable. We're saying, okay, when I'm inside this function, I want a bit of space that I'm going to call temp. It's going to store a struct node. What happens when you exit this function? That was temporary storage. It's gone. And the next time I call a function, it may use that same location in memory for my temporary variable. There's no guarantee that the memory that's being used for any local variables in here is stable once we exit this function. It might go away. It might get used by something else. It might get reused next time we come in here. So if I call this 100 times, it's possible that each time I'm going to return exactly the same address. And I think I'm creating 100 nodes, but I'm creating one node 100 times, which means the first 99 values that I stored in my nodes just kept getting overwritten by this. So this will compile, and it will work if you just call this and you come back and you look at the value right away without doing anything else. But we're not actually creating new nodes. So we really need that call to malloc. That's how we actually synthesize new stuff. And every time we call this, if we call malloc inside here, we get a new block of memory at some different location. If we call this 100 times, we'll actually have created 100 distinct nodes at 100 different locations in memory. And they'll all exist. And hopefully we've linked them together so we have a way to get to them, but maybe not. But even if not, they still exist. All right, well, malloc is used to get memory from the system. The counterpose to that is free. And free is used to release memory that we've malloced. So if we want to create a node, we use malloc. It gives us the address of a block in memory. We do some stuff with that. We put values in it, whatever. If at some point we decide we're done with that node, we don't want to use it anymore, we should pass the address of that node to this function free. And that basically does what your release node does in PA1. It clears a valid bit somewhere and says this block is no longer in use. And now the next time you ask for a block of memory, you might get that same block back, which presumably is okay because you called free because you didn't care about what was in there before. If you never call free, every time you call malloc, it grabs another block of free memory. If you never call free, it just keeps taking more and more memory, and the available memory drops and drops.
Until you eventually get full memory.
Until you eventually get full memory. And then you call malloc and it returns null and says sorry. Now if your program exits, all the memory gets freed. But what if your program never exits? What if your program is serving up web pages, and when you boot your machine, it starts running and it runs until the machine is shut down? If it's got places where it's allocating memory, and then when it doesn't need it, it just doesn't bother freeing it, the memory will drop. And if you look at the task manager or whatever your utility is, you'll see free memory going down, and eventually the system starts performing worse and worse. So this is called a memory leak. Okay, a memory leak is when you allocate memory and you don't release it when you're done with it. If you allocate 1,000,000 bytes of memory, that's not a leak. Okay, even though it might be a lot of memory, it's not a leak technically. The leak is, I need a block of memory, I'm done with it, but I don't release it. So I've got some memory that I don't need, and if you do that too many times, you can run out of memory. So we try to pair freeze with malloc so that when we're not using this block anymore, we free it. So for our linked list, when would we want to free? We want to free when we say delete. You delete a node, you adjust the pointers to skip over the node you want to delete, but then we also are going to want to call free on that node to say, hey, we don't need this storage anymore. Put it back in the free space pool, and then sometime later when we call malloc, we can reuse that. That's what release node does in PA1.
So in free, do we put the pointer?
You put the pointer, right? The pointer that you got from malloc. If you put something that's pointing somewhere else, free will get unhappy. And it's fairly easy to get memory leaks. It's not too bad in our linked list because there's only one place where we want to release memory, which is when we say delete. And you're already saying release node in PA1, so you'll just say free in PA2. And then at the end of your program, you'll want to release all the memory, and we'll talk about how to do that later. But you basically just go through your list and release each node that's in the list. But as the structures get more complex, and you have things pointing to different things, and you have multiple things pointing to different things, it becomes a little more subtle sometimes, knowing when you should free something, and where you don't want to free things too soon, because once you free a block of memory, that block is subject to change. But if you don't free it when you're done with it, you can get a leak. So we'll also talk about a utility called valgrind, which we can use to find memory leaks in our program. So valgrind will run a program, but it will monitor how we're allocating and freeing memory, and it'll let us know if we've got leaks in the end.
In other languages, do garbage collectors?
This is what garbage collectors take care of for you, yeah. So in some languages like Java, for example, we don't actually call malloc and free. When you want a new structure, you just go ahead and you say, give me a new structure. Here's the danger with, not the danger, but here's the main issue that leads to memory leaks. So pointer equals malloc. And we do some stuff. And then somewhere else we say pointer equals, something else, pointer.next. Well, so we had a block of memory that came out of malloc, and pointer was pointing to that. And then we go ahead and we said pointer equal to pointer.next. Okay, from the current value of pointer, there's nothing that gets us back to this block. Hopefully we have a variable like sentinel or header that's pointing to this, or we have some node before this that's pointing to it. But it's possible, if you don't write your code just right, that we no longer have any variable that refers to this location in memory. And we have no way to find that location. There's nothing pointing to something that points to this. And so it's a lost block. We changed the thing that was pointing to it to point somewhere else, and we don't have anything else that was pointing to it. And there's no way to get to this. And now you can't free it, because we don't have an address to pass to free. So that's considered a permanently lost block. So Valgrind will run through your code, and at the end it will give you a report. And say you allocated 52 million bytes, you freed 51,999,950. You had 50 bytes that were left over. 20 of those were permanently lost. We had no pointers to them. 30 of them could still be freed because you had things pointing to them. And it'll give you a nice detailed synopsis like that. So, languages like Java take care of this for you. When you create a new object, you say new, it's basically doing a malloc, but it's keeping track of how many things are referring to that object. And if I do something like this, like change PTR, and there's nothing else referring to this, it'll automatically free that memory for me. So there's a thing called a garbage collector that runs in the background, and every now and then it goes around and looks for things that aren't in use anymore, and it reclaims that memory. C, we got to do it ourselves, just like everything else in C. But Valgrind will make that fairly painless. All right, so let's look at some pseudocode. So in our main program, our linked list is going to be a struct node star. Okay, it's not going to be an array, which is still a struct node star, but it's just going to be a pointer to one struct node, which will be the sentinel. So our main program would do something like struct node star LL. And this is the pointer to the linked list. Pointer to the linked list. And so we can say something like LL equals init. And init might create an empty linked list for us. So what's an empty linked list? It's a sentinel node. So maybe a magic value like dead beef in the data value, and then a null in the next field. And so LL points to the sentinel. That's our initialization. So let's just look at a print routine. So our print routine would take one argument, which is the linked list, which is actually a pointer to a struct node, which is a pointer to the sentinel. And print doesn't return anything. So we could make it a void. So void print struct node star LL. Well, let's make a picture of a bigger list. and this is the sentinel. So our list really contains two data nodes, a 10 and a 20. And when we call print, LL is this sentinel node. So this is where this tension comes in, where I'm writing LL as if it's this box, but it's actually a pointer to this box. Okay? And when I say this is previous and this is current, those are pointers. But if I write current over here, I mean current is pointing to this node. If I write previous over here, I mean previous is pointing to that node. So how do we print out this list? What's the first node in the list? If LL is the sentinel, how can we write an expression to describe the first node?
Whatever the sentinel is pointing to.
Yeah, whatever the sentinel is pointing to. Whatever the next field of the sentinel is pointing to, right? So LL is a pointer to a struct node, so we want the thing that LL points to, we want the field name next on that. And that's LL arrow next. So LL arrow next is basically this node. So let's make a variable. And I'll call it current. And I'll start the whole process by saying current equals LL arrow next. So now I'm going to write current above this node.
And we want current to be a structure.
Current is a structure. It's a struct pointer to a structure. All right, so we're going to loop. The first thing we want to print out is current's data. All right, so print current arrow data. Again, what we mean is current is a pointer. Take the thing it points to, give me the data field. So if current is pointing to this node, the data field is 10. And then we want to move current down to the next node. Exactly the same thing we did when we started. Set current equal to current arrow next. So now current is going to point to this node. Print current's data, that'll print a 20. Set current equal to current arrow next. Well, this time current points to this node, the next field is null. So now current is equal to null. And I better stop. Because if I say print current arrow data, it's going to say take the thing that current points to. Since current is null, which is 0, it's going to say go to memory location 0. Tell me what's there, segfault. So this whole thing becomes a while loop. And we can safely house it as follows. Well, current is not null. Bless you. So when you're writing this, you have to have pictures. You write your pseudocode or C code, and you have to check your edges. So what are the edges? Well, the main edge case here is when the list is empty. So if the list is empty, what does it do? It says current equals LL arrow next. That sets current equal to null. While current is not null, never executes the while loop. So we come straight down here, and we can just return. And if list is not empty, current will start off here, print a 10, move current here, print a 20, move current to null, exit the while loop, return. That does the right thing too. You're probably in good shape. But if you're getting errors, go into GDB. So write your code, set a breakpoint at print, run it, do your print command. When it gets to print, it'll come back and say, okay, what do you want to do? And start stepping it or nexting it. And print out the value of LL. Examine memory at that location, make sure it's your Sentinel node. Execute this instruction, make sure current is pointing to the first node of your list. So examine memory at that location, see if it's got a data value. And if it does, right, next your way over the print statement, it should print the data value. Set current to current next, make sure that's what it should be. And you can use the examine command in memory or the p command, and you can actually see your list in pieces. So we'll play with that. Well, we got some time. We'll play with that tomorrow. Let me make a note. That'll be fun, actually. All right, so we'll mess with GDB more. I'll make some lists in memory we can play with. I'm also going to do a group activity at some point in this class, a few group activities, where I'm basically going to give you some dumps of memory and ask you to do some analysis on it, on paper or on the board. This will take the place of having labs in here, but we'll play with GDB and see how that works. All right, so questions about this? This is in general. No, it's not for the ODP. It's pseudocode for PA2. This is exactly the same algorithm we did a week plus ago when we talked about how to traverse a linked list. The code is different in C, but the pseudocode, the algorithm, is exactly the same. Start with the thing the Sentinel points to. As long as that's not null, print its data, set your temporary to what that points to, and iterate, and then return at the end. Now the implementation is different because we have these arrows to dereference these structures, but the logic is exactly the same. And it's going to be the same for adding and searching and deleting and initializing. So PA1, you're mainly learning about the linked list piece. PA2, we're mainly practicing with how we work with dynamically allocated memory to build up a list where these nodes are scattered around in memory. And what's going to happen when we actually develop this program? Well, what is memory? It's kind of like a big array going from 0 to 16 billion if you have 16 gigabytes of main memory. It's a 16 billion element array. And what's stored at location 17? Well, that's just the entry of element 17 in this 16 billion byte array. So main memory is kind of like an array. And when we say call malloc and give me the address of a node, it's kind of giving us the address of an index in this, an index to an entry in this big array of 16 billion bytes. And when we do this dereferencing, right, if pointer 17 and we say star pointer equals 100, which writes 100 right here, it's kind of like saying you know, this big memory array bracket PTR equals 100. So in some sense, pointers are really no different from array indexes. It's just the array we're talking about is the array, which is your main memory, which houses everything. But if you think of it like that, it's kind of the same thing. So you've sort of been doing pointers and pointer dereferencing in PA1. We've been doing it with arrays. And we'll do it explicitly in PA2, but we can think of it like this too. All right. Well, we can continue with pseudocode because we're a little bit ahead of schedule here. So my goal is to run through pseudocode for doing these things with this approach to storing nodes instead of an array with structures with 3 fields. So go through pseudocode for our functions with this type of node, and then spend some time in GDB practicing with GDB, but also using it to look at some structures in memory. And I want to do that basically the rest of the day and tomorrow. Friday I want to spend talking about PA2. There's no class on Monday, so you have like a 3-day weekend, which, whatever else you're planning, is a good chance to get started on PA2. So I want to make sure we get through that and answer any questions. And I'll give you one more ODP. That'll be tomorrow, and I think that'll be it. I think I'll hold off on giving you one for the weekend because I'd rather you think about PA2. And then next week we'll start in on other details of linked lists. So pseudocode. So we know how to print. How do we search a linked list using these structures? So
You have to traverse the list.
have to traverse. So here's LL. And we've got this chain of blocks, chain of nodes pointing to other nodes. So again, start off with the first node. And I'm switching to some pseudocode here. So while the temp is not null, and our search takes 2 arguments, also needs a number. So if temp's data is equal to number, return 1, saying we found it. Otherwise, move down the list. That's just the same thing we did in traverse. Temp equals temp. Next. And try again. Temp's not null. Does the data match our number? If it does, we found it. If not, move down the list. Does it match our number? If not, set temp equal to temp next. Well, at that point, temp equals null. And that's where we exit our while loop. If we had found the number in our list, we would have returned 1 at some point. The fact that we got through our while loop without returning means we didn't find our number. So just return 0. And again, that's the same pseudocode that we had for PA1, except we said temp.data and temp.next. So PA2 is going to look really, really similar. Now, when we converted from pseudocode to actual C code in PA1, temp arrow data became something like LL bracket temp dot data. Temp arrow next was something like LL bracket temp dot next. And temp was an integer instead of a struct node star. And when we have our structures,
What's that in the purple?
sorry?
What's the stuff in the purple?
Oh, weird, that's red. That's how we would have written this in PA1 if we were actually implementing this with an array of struct nodes. But if instead of the array we're just using memory locations, we just use this arrow to dereference and pick off a field. All right. Keep plugging away on PA1. How many people are confidently close to done or done with PA1? Okay, that's not bad. All right, keep plugging away with that. Bring questions tomorrow, okay? Don't plan on emailing me at midnight Thursday night with questions, okay? Try to figure out where you're stuck and either come and see me or bring them to class tomorrow, and we'll work through them.